So how fast do molecules actually move? Well, that can be determined based off of the root mean squared velocity. So just like with bigger objects, the velocity or the kinetic energy of molecules is equal to 1/2 mass times the velocity squared. What we end up doing in chemistry is calling that velocity URMS. That's the same thing as a velocity, but the RMS stands for root mean square. So basically what they do is they take the velocities of all of the molecules and they square them. Then they average them, which is taking the mean, and then they take the square root of them. So this is some statistical method that is above your level. Don't even worry about it, but just know that this URMS is the same thing as velocity, but it's kind of more of like an average velocity, right? Because some molecules, if we look at this graph over here, some molecules, let's look at the one at 0. Some molecules are moving slower, some molecules over here are moving faster, and as we heat it up and get to higher temperatures, we shift. So the peak or the majority of the molecules are moving at a faster speed compared to when they're at a lower temperature, they're moving at a little bit of a slower speed. And so we can check out the area under the curve is representing how many molecules we're dealing with at that particular speed. So when I'm cooler, I have more molecules moving at a slower temperature overall compared to when I'm at a higher temperature, more molecules are moving faster. But we have a whole variety, right? So some are moving slow, some are moving fast, but the average is kind of that peak, that tip of the tip of the curve where we're getting that the most common or the average speed. So what we use is that we use the equation that kinetic energy for molecules, so gases at the same temperature, is 1/2 the mass of the atoms times by the root mean squared velocity squared, right? So, and what we could also do is there are two equations, I'll do them down here. There are two equations for kinetic energy. First equation is the one I just did. Kinetic energy equals 1/2 mv, which root mean squared velocity squared. The other one is related to temperature. It's 3/2 RT. Because we know that kinetic energy changes with temperature, but in this equation, in the first equation, it doesn't say that at all. It just has, right, mass and velocity. So we can combine the two equations to get the overall one we're going to use. So we're going to set these two equal to each other since they both equal kinetic energy. I'm going to do 3/2 RT equals 1/2 m URMS squared. And then I'm going to solve for the speed. And doing this is going to help us to relate the speed of the molecules with the temperature and the molar mass of the molecules. So we're going to solve for it. I'm going to divide by 1/2 and by mass. So I'm going to divide by 1/2 and mass. And dividing by 1/2 is the same thing as multiplying by 2/1. So notice the 2's cancel out. Cross out that whole thing. So URMS squared is equal to 3RT over m. And then we can square root the whole thing to get the overall speed. So this is what we will use, is that the root mean squared velocity is equal to the square root of 3RT over the molar mass. So what this means is that as the temperature increases, our speed increases. As the mass increases, so as we have heavier objects, the speed decreases, right? Because mass is in the denominator, and so if we get a bigger denominator, it lowers the overall speed. So a gas with a low mass, its speed will be faster or greater than a heavier molecule. Some key things I want you to keep in mind, though, is that we have a couple unit issues. So the R we're going to use is energy R, because we're dealing with kinetic energy here. The R that we've been using is when we have atmospheres and liters. We don't have any atmospheres and liters. We actually have kinetic energy is measured in joules. So R that we're going to use is 8.314 joules per mole Kelvin. And it actually is derived from the other R, and I can show you in another video or in class. You might see that derivation. So since we're in joules, a joule is a kilogram, just FYI, a joule is a kilogram meter squared per second squared. And so we need to make sure that our molar mass here is in kilograms per mole. So what I like to do, I'll show you in the next problem, is I like to just in that or in this equation, convert into kilograms. So let's practice this. We're going to calculate the root mean squared velocity of molecules in a sample of nitrogen at 25 degrees Celsius. So we have nitrogen. It has a molar mass of 28 grams per mole. And the temperature here is 25 degrees Celsius, which if we add 273 will be 298 Kelvin. So if we do URMS equals square root of 3RT over M, we'll plug that in with our values. So we get 3 times, and remember we're using the other R, which is 8.314 joules per mole Kelvin. And then our temperature is 298 Kelvin. And then our molar mass is 28 grams per mole. But we need it to be in kilograms, like I said, so we're going to just divide by 1,000 grams per kilogram. Which ends up, you could do that up here too, it ends up being 0.028 kilograms per mole. So we're just moving the decimal over 3 places. On the side here, I'm going to show you how those units cancel out. So I'm just going to do the numerator first. A joule, as I mentioned, is a kilogram meter squared per second squared. Okay, that's the joule. So we have a joule per mole Kelvin for our gas constant. We multiply it by Kelvin with our temperature, and then we divide it by kilograms per mole. So what we end up getting here is that our kilograms end up canceling out our kilograms, our Kelvin cancels out our Kelvin, and our mole cancels out our mole. So what we are left with is meters squared per second squared, and we're actually going to take the square root of that, right? So we end up getting meters per second. So when we plug that whole thing in, you should get 515 meters per second. So those molecules are moving fast. Let's try the speed of an atom of helium at the same temp. So here we're going to use the exact same equation. The only difference here is that helium has a mass of 4 grams per mole. So we can do that conversion here or elsewhere. I'll do it here this time just so you can see. We end up getting 0.004 kilograms per mole. Now helium is much smaller than nitrogen. So since it's a lighter molecule, we expect the speed to be greater than 515 because it's lighter. So we'll put into our equation URMS equals the square root of 3 times R 8.314 joules per mole Kelvin times 298 Kelvin divided by 0.004 kilograms per mole. We know the units are going to work out. So I encourage you to plug that in your calculator. And when you do, you should get that the answer is 1363 meters per second. And then the last thing with this section is dealing with effusion and diffusion. So effusion is when molecules of a gas are going to escape through tiny holes into evacuated space. And evacuated space could really just be a low pressure space. So when we have something in high pressure, like up here, their molecules are bouncing in and they're going to escape through tiny holes and into the low pressure space. Diffusion, on the other hand, is the spread of a substance throughout space, or a second substance where, like, it could be like water, for example. So if you ever put food dye in water, you can see it diffuse, those colors diffuse throughout the solution until it kind of mixes. Or if you spray perfume, you know that over time it's going to get to the other side of the room. Okay, so Graham's law relates the molar mass of two gases to the rate of diffusion, and what we see is that the lighter gas always goes faster. So we see here, initially we have argon and helium. Now they have different molar masses, so argon is actually heavier, which is why it sinks, versus helium. We can see that helium actually gets, a lot of the gas molecules escape, making it sink, where argon, if those gas molecules escaped, it would rise up. And so helium's, because it's lighter, the molecules are going to diffuse or effuse faster through the holes. So the equation we're going to use is that the rate of one molecule over the rate of another molecule is equal to the molar mass of the second molecule over the molar mass of the first. And this actually gets derived from the root mean squared equation, where if I take U RMS, which is a rate of molecule 1, over U RMS of molecule 2, we do square root of 3RT over M1 divided by square root of 3RT over M2, and we can see that the 3RTs are going to cancel it out, and we end up getting 1 over square root of 1 over M, or M1, and divided by 1 over the square root of M2. So a denominator of a denominator becomes a numerator. So we end up getting the rate or the speed of one molecule over the rate or speed of the other molecule is equal to the mass of the second molecule over the mass of the first. So I very much encourage you to write down which molecule you're talking about. Which totally leads into this next topic. So in this practice problem, it wants us to find the ratio of the fusion rates of nitrogen gas and oxygen gas. So the number you get is going to be dependent on how you write the equation. So if I write R of nitrogen over R of oxygen, then my number is going to be different than if I write the ratio for rate of oxygen over the rate of nitrogen. So in this problem, it doesn't necessarily tell you which one's on top. It's okay either way. In some of the homework that you'll have, it'll tell you what the ratio is, who's the numerator, who's the denominator, and that's how you should proceed in your calculation. So I'm just going to do this top one. Rate of nitrogen over rate of oxygen is going to be equal to the square root of the molar mass. Remember, the bottom one comes up top, so molar mass of oxygen over the molar mass of nitrogen. So they just switch spots. So we can then plug in our values. The molar mass of O2 is 32 grams per mole. Molar mass of nitrogen is 28 grams per mole. So when we plug in that, we do 32 over 28, and then we square root it, and we get 1.07, meaning that nitrogen is going to effuse at a rate that's a little bit faster than that of oxygen, right? Because it's bigger than 1. And that makes sense because nitrogen is a smaller molecule, so it should move with a higher speed and effuse at a higher rate. Now this problem is a lot more fun. It has, so we have an unknown gas, we'll just call it X. Okay, it's a homonuclear diatomic, so we're actually going to call it X2 because it's a diatomic molecule, and it effuses at a rate that is 0.355 times the rate of oxygen, which literally means that the rate of this unknown compound is equal to 0.355 times the rate of oxygen. All right. So this helps us to set up the ratio that we have here. So we want to get the rates on both sides, or both of them, sorry, on one side. And so we're going to divide by RO2, the rate of oxygen. So then we have the rate of our unknown over the rate of oxygen equals 0.355. So there's the number, just like we found the number up here, right? That's the number that they are giving us. So this value equals the ratio of the rates, which is also equal to the ratio of the molar masses. So here I'm going to put the mass of oxygen up top over the mass of the unknown. So let's plug in some numbers now. We have 0.355 equals the square root of 32 grams per mole over the molar mass of this unknown. We can then solve for the mass of the unknown. So to get this guy all by itself, we're going to, first thing we need to do to isolate it is we're going to square both sides. That's going to undo the square root. So we're going to have 0.355 squared equals 32 over the mass of our unknown. And then we want to get the mass of the unknown by itself. So what we want to do is we want to multiply that guy up and move this guy down. So we're going to multiply our mass of our unknown up and divide 0.355 squared down, giving us the mass of the unknown equals 32 over 0.355 squared. You could plug that into your calculator, and then you get the mass of the diatomic to be 254 grams per mole. Now it does say it wants us to identify what this unknown is. So what we want to do is look at, if this is the mass of x2, then what's the mass of just x? We'll do 254 divided by 2 to get the mass of just x by itself, and that will give us 127 grams per mole, meaning that the identity of the molecule, or this atom, is iodine. So the molecule that they were studying was the diatomic iodine squared.